operator L is split into a local and a non-local part. So pieces that are on the diagonal and that operating in the same mesh point, and another part that operates outside, away from the mesh point, the same mesh point. That's a non-local part. The non-local part is taken from the previous iteration. The local part is a composition of the current time as a new iteration and the previous iteration. And Gauss-Seidel means basically that the two have the same weight, and successive over-relaxation means that the future time has a higher weight by a certain factor which can be calculated. It's called alpha in the numerical recipes. It's 1.7 or something times more than the other one.
It's a sort of extrapolation. You know how the correction goes from one step to the next step, and you sort of extrapolate it.
And then there is a method which actually reduces again this over-relaxation factor, this time. It's also quite something fancy.
That's significantly more complicated than just doing the simple iteration scheme. And I think until multigrid came up, that was one of the methods that one could really use to solve such an elliptic problem. Whereas with those methods, you basically don't get anywhere as soon as you have significant resolution. But here, the multi-grid, the interplay of the different grids does the job. So you want something fast for the individual smoothing step. And so some time has passed since I read up on all of this. I might be mistaken, but I don't recall that people really plug something that fancy into a multi-grid scheme. I might be wrong, but the philosophy basically is you do something that does a good job on the small scales, and you don't need more than a simple iterative scheme there, and then let the multi-grid method, the interaction between the grids, take care of the rest. So I think this is more complementary. A successive over-relaxation is one way of doing it, but multi-grid is a typically more efficient way of doing it.
Well, it's part of the whole thing. I mean, the Gauss-Seidel is part of your thing, and successive over-relaxation is just a very minor modification on your point 3, I think.
Maybe one can combine the two and really gain something, but this, if you do these sweeps here, you get a different dynamics, different damping behavior for the individual modes than you would get for Gauss-Seidel. So probably one would have at least to adapt it again.
But did I not understand correctly that Gauss-Seidel is simply part of your scheme?
Yes,
that's part 3.
Yes,
exactly.
Yeah. But without over-relaxation. I'm saying if you do over-relaxation here, you might not gain much, but unless you do it in a way that's really adapted to the way the arrow goes here. So, but I don't know much about that. Okay, and then now we're on the smallest grid again, and now we can just do the whole thing over and over and over. I sort of elegantly skipped over one step here, and that's we have the fact that we have a linear system of the same structure as the original one, this one here, and I just assumed that this time on the causal grid we can solve that. Point is, if we can't, we go to a yet causal grid, and the yet causal grid, until we really are on a grid with only a few grid points, and there the iterative scheme does quite a good job. So if instead of that just describe two-grid model, a two-grid method, one stacks many more of these grids onto each other, on top of each other, and that gives you a multi-grid scheme. All you really need is this thing here, and this can easily be coded in a recursive manner, because at every grid level you go to the causal grid, and then you do basically the same thing. Okay.
Yes, maybe there is a compromise between the time you lose in the interpolation stuff and the resolution of the primary problem, no?
I find that with my implementation, the bulk of the time is actually spent in the Gauss-Seidel iteration. interpolation is not such a big deal there. I'm not sure how characteristic that is, but unless I get the principle really wrong, I guess it is probably generic. So interpolation is not so much the problem.
Slightly surprising, huh? Because there are two mildly non-local operations. I mean, near neighbor and related operations, interpolation and outside. I'm surprised.
Maybe I got something wrong with the.
Oh, maybe the interpolation is not. You don't need a very good interpolation when you go from one grid to another grid. Maybe
you need if you have a second order derivative operator in your equation, like here, then you need at least linear interpolation. If you have a fourth order operator, then you need at least cubic interpolation for the whole thing to make sense. But what I'm doing here and what people generally are doing is just trilinear interpolation. I played with line interpolation in 1D and it made a minor difference, but it didn't change much. So first order interpolation is just fine.
And it converges in how many steps?
20, 30. The error just goes down exponentially, and at some point you reach 10 to the minus 6, which for a test problem where the initial or the characteristic value would be 1 means that what I have curves like that. I don't think I have any of that here, but you really get an error. Well, this is I iteration, and this is log. Well, say that can be the residual. That's the quantity we can easily monitor because we're calculating it anyway with any normal the residual will do. Then you find that this goes in. Well, initially there may be some irregular behavior, and then it goes very nicely exponentially down. And then at some point you're just at the Brownov level, and then it levels off.
But again, you sure for a very large problem, I agree that's certainly a good thing to do. But did you compare the time the cost of this method compared to solving, inverting the big matrix of the beginning?
The matrix can't be big, or you can't invert it. I haven't done the estimate, but let's see, well, okay, it depends a bit. If you take care of the fact that, if you take into account the fact that it's a sparse matrix, which you probably should, but which makes things technically really nasty, then you probably could even do that. But I'm not sure. Probably the sparse matrix solvers do something that boils down to a similar method behind the scenes. If you use a full matrix, then if you have say 100 cubed, then you have 10 to the 6 points. Then your matrix would have 10 to the 12 entries. There's just no way you can invert that. So there is no simple matrix method that works for problems that are not really toy models. I don't have any time. It would be interesting to compare this with the Fourier stuff, even though the boundary conditions are different now, but it shouldn't be difficult to implement periodic boundary conditions here, and the workload shouldn't depend much on that. So probably I could just take this and at the same resolution do the Fourier stuff and compare that, but I haven't done that.
Yeah, but in this case you can have a nonlinear problem and variable coefficient.
Yes. So it's not really like you choose one or the other, but sometimes you can't use Fourier.
Yeah. I think I want to make a comment. Not grid is not really good for periodic boundary condition. No. The convergence rate will be very slow when you are using periodic boundary condition.
Why this?
I'm not sure. This is for my own testing. I found the convergence rate is very slow.
So
I think it's the problem goes down to the courses grid. You have no solution at no exact solution at the courses grid. A multi-grid, the power of the multi-grid, one of the powers of the multi-grid is that you can have the exact solution at the courses grid. And use that, you can even speed up your algorithm. And with periodic boundary condition, there is no exact solution at the courses grid.
But why? I mean, you can always invert the matrix. Once you're down at a
No, there's
close
no.
enough,
I
you can invert the
think
matrix.
that at the courses grid, it's singular. The solution is singular. Take Poisson equation for example at the courses grid. I think the matrix is singular, and you have no unique solution for that.
I mean, maybe that can be true. I mean, for a periodic mesh, you have a 2 by 2, right? It's just up and down, plus and minus, right? In that matrix, you're saying now a singular, right?
Because
So I
periodic
think that
boundary
could be true.
condition.
You have indices 1, 1, and 1, 1 maybe. So therefore, the determinant is 0. Is that basically what you're saying?
Yeah, that's
But
right.
I don't see that. If you have...
But maybe then we can take the next courses grid, where you, I mean, 8 by 8 or 4 by 4 rather, of course. And
Then
don't-
you need, then you cannot have the exact solution. I would say.
I think,
But I mean, what
it
if-
should
what-
be not so difficult. A 4 by 4 matrix, you can
You
write down.
still need a numerical method to infer it down.
4x4 matrix. That's no
Yeah.
problem. But I mean, I don't see things becoming singular here, because this point is identical with this one, because we only really have 2 points. So that
Mhm.
this is no. This here is the other boundaries. Then you do have a non-zero second derivative here, which is positive, and you do have one here that is negative.
No, I haven't done this, but you said you've done it. Yeah, I'm just imagining what could be the reason.
Yeah, as far as I recall, that's the problem. So, I think the comparison should be go to other boundary conditions. If you want to compare multi-grid with a Fourier transform, that's my problem here.
Okay. Right, let me go back to this one. Okay, here's the same recipe again, and now with somewhat more detail. One thing is we can easily put a scalar function of a function of x here, an additional one, and we can still use the same method. If you use that equation, which, well, here I call it inhomogeneous Helmholtz equation. I think it's only a Helmholtz equation strictly if this one is constant. So you can consider this a generalized Helmholtz or a generalized Poisson equation. Probably doesn't have a name I know of. If you discretize this, then basically you have these 3 second order derivatives. If we go to second order, you just take the neighboring points and use and the point itself and use the weights 1 minus 2, 1. And you might have different grid spacing here, although that often easily causes problems with convergence. And then you have just this G term multiplied by F just at the very grid point that at the very central grid point that we're considering, and then you evaluate the right hand side at the same point. And I haven't written out the expression here, but it's not too difficult to then collect this term, this term, this term, and this term, because that's all the value at the center of our 3-directional stencil. And put everything else on the right hand side, and then you get an equation Fijk is equal to, and then you have some linear operator that operates on F, and that turns into the game all the neighboring points. And in addition to that, there's also the constant contribution at the end. And just going through all the grid points to all the points in your grid and applying this and immediately updating the F for the right-hand side after each step, or updating it and working with that updated copy. That's just the Gauss-Seidel method. And then there's variants. There's red, black, Gauss-Seidel, which I haven't found any reference of why or whether really that should be better. So I think that there's lots of cargo code around the whole thing, and I implemented only the stuff that seemed to make sense to me. And yeah, here's an attempt of writing this iteration scheme, but that's just the thing that I talked about. Okay, in the literature you find lots of applications, lots of discussion of a different iteration scheme where you do not update in real time, but you calculate the new F values for the whole grid based on the old F values that you had, and only then you update. That's not interesting in practice. Well, first of all, if you do it exactly like this, you don't get rid of the very smallest scales, don't get rid of the Nyquist scales. You can do this partially. You can calculate this new F based on all the old F on the right-hand side, and then you can combine the two with a relative weight of, I think, 2/3 for the new one and 1/3 for the old one. This is what people like. And then it does damp the Nyquist scales, but mostly people discuss this because it's easier to analyze mathematically. There's no advantage and a big disadvantage in doing that in practice. And the disadvantage is that you need more memory. But first of all, you need more memory. Second, it actually converges slower. This method, as such, without the weighting, converges 2 times slower. It takes these 2 times more iterations than the Gauss-Seidel method. So there's no point in using that, unless you really want to analytically understand the iteration process. Okay, here's the weighted scheme where you introduce that weight. Well, that's not so interesting. Now, coarse graining or restricting, or I think there was an even weirder name for that. Basically means we go from the finer grid to the next coarser grid. So imagine we have values, the values here, 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 and here, and we want for the coarser grid the value here, and the value here, and the value here. Now in the easy you could just take the value that you already know for that point and move it up, well, carry it on to the coarser grid, but that's bad because if you go from that grid to the finer grid, you need to get rid of all the scales that you cannot represent on this grid. So you really want to apply a filter that, if in wave number space, if this is the Nyquist frequency for the fine grid, then the Nyquist frequency for the coarse grid will be here. So if you have signal all the way up to the Nyquist frequency on the fine grid, you need to apply a filter that tries to keep the large scales, but to ideally completely damp out the scales that are beyond this. And if you use an interpolation operator that just uses the neighboring points, then it just means that you smooth the information you have on this grid with a relative weight of 1, 2, and 1, and that's in a sense optimal. And you could figure out filters that do this even better if you go further out, but again, that doesn't seem to buy you much in terms of convergence, and it's just more effort. This is called, what is it called again? Has a name. You'll see it.
The weights might 1, 2, and 1 are applied to the fine mesh box. There's nothing overlooked.
Fully weighted.
You don't jump over neighboring points here in the finer mesh. You take all the points on the finer mesh take 1 to 1.
All of them enter the signal up here, yes. Which is important, and actually they enter if you sum up the signal here, they enter all with the same weight. Because this one enters with a weight of 2 or what? You have normalized, so the weight of 1/2 here. This one enters as 1/4 here and 1/4 there, so in the end it is also present on the coarser grid with the same total weight, and that's important because that means that the integral of your signal is not changed. And that means that we don't affect or damp the very largest scale, which is the scale where everything counts. That's all very nice and simple, and all the books write about this fully weighted smoothing. That's the name of this method. But what the books that I had hardly talk about, and the papers that I found, is the case that we have with the pencil code. Look at the number of points here. Here we have 2 points, okay, that we can do with the pencil code. On the next final grid we have 3, then we have 5, then we have 7, and then we have, 9, and then we have 17. Did anybody here ever do a simulation with 17 points in any direction? Probably not. And even, no, 17 would work fine. Basically, 2 to the power of n plus 1 would work fine. But we normally use 2 to the power of n. We have this situation for the periodic runs. Because basically what the grid points here are of the coarser grids, are grid points of the final grid as well, because the number of intervals is a power of 2. We normally have the number of grid points a power of 2. If we use periodic boundary conditions, that's the same thing. So that's actually a case where, we have this situation. But for non-periodic boundary conditions, we have this situation. So instead of 17 points, we have 16, 8, 4, 2 points. And now you see that this point here of the coarse grid is not the point of the fine grid. So we cannot directly use this fully weighted smoothing. So what I'm doing now is I interpolate I think I interpolate everything on the finer grid, although that right now doesn't seem to make much sense. I probably played with both options. But basically you can use, oh no, I know what I do. It takes significantly more memory than this does. That's what I remembered. But still I interpolate, I use fully weighted smoothing to get from this point up here, from this point up there, up there, up there, up there. And then I interpolate from those 2 or probably 3, no, from those 2 points I use the same trilinear in 3D interpolation routine to get to the value here. And that seemed to work fine, and that converges somewhat slower than if you have a grid like this, but it takes a bit longer to converge basically, but the convergence rate seems to be the same. And I found very little on that in the literature, and I don't recall the details. I think whatever I found basically seemed to indicate other people are doing the same.
I think I can propose a different way of cell-centered grid. Just think of it as the finite volume cells. Then you can just restrict the 2 points into 1. Not fix the boundary point at the same position, but for each pair, just map into 1 and at center. So you will have a triangle-like grid structure.
You mean like for this point, just take those 2 points? Or? Right. Yeah, but you want to have something that is a line that is similar to this here where you have 3 points. So you should have at least have 3
That
points.
doesn't matter, actually. That doesn't matter.
But if you only use 2 points, you screw up this filtering property. You get a worse filter.
No, actually no. No. In practice, no.
But then I could do the same thing here. I mean, I could think, okay, this point is slightly just by a femtometer to the left of that, so I only use those 2 points. Would that work?
I didn't get you.
If I can do with 2 points here, I can do with 2 points there. I only use those 2 points to coarse grain, to get this coarse grain value. Would that work?
You would lower cross interpolation already from 2 to 1.
No, what I'm saying is
And then he's probably saying that doesn't matter.
what I'm saying is that actually think of this as the finite volume sense. In finite volume sense, you have one cell. You have two cells that you want to restrict into one cell, then just sum it up and average make the one cell. And this is equivalent to these 2 grid points map into this one.
But the cells really are like this.
No,
there's a contribution from another cell.
no, this is because you fix the boundary point at the same position.
Yes.
That's
what we're doing.
What I say is that don't do that. But you have 4 grid points and map even for the boundary point into here. And you got 2 and 2. So this will always the multiplication of a power of 2.
And it's basically the same thing. But this is no longer going to be a boundary point, so we would have to reformulate all of our boundary conditions. Of course, you can do that, but right now we know that the outmost point here is a boundary point. So we formulate we populate those cells based on that. So you are right. That would solve the problem, at least if we always calculate with powers of 2 for the number of grid points. But it would be incompatible with what we're doing.
Yeah, I see what you meant, because of periodic boundary condition.
Yeah, that's
Okay.
the problem. And based on that, I then decided that the good thing is this is so general that it is more work, but it is so general and it doesn't seem to degrade the performance or the conversions overall. I can't really talk about the computing time spent on that, except that profiling showed that it's the Gauss-Seidel stuff that dominates the computing time. Anyway, the other advantage is it allows us to not just use powers of 2 for the number of grid points, but now we can use everything. So in that sense, it's more robust. It's less constraining. But yes, that would have worked with a different way of writing the boundary conditions. But it would really need to mean that we would have to change the way we're doing it.
I do really want to know what's your testing results on periodic boundary conditions. And I would suspect that the same problem I encounter will be the same. The convergence rate will be very slow. Even if you do anything about the restricting and smoothing. That's my guess.
As I said, currently I only have coded Dirichlet boundary conditions where things are nice. So everything is 0 on the boundary, and that looks nice. But I haven't coded the periodic boundary conditions yet.
I would like to know.
Dirichlet is really French, right? So
I'm sorry?
Dirichlet is French, right? How does the Frenchman pronounce his name? Dirichlet is French, right? In American you say Dirichlet. And in Deutsch, Dirichlet. Is that French?
Oh, it's
Dirichlet. Oh.
Dirichlet? Is that Dirichlet? Oh, it's
How do you say
Dirichlet.
it?
Dirichlet.
Yeah, Dirichlet.
Dirichlet. Yes, Dirichlet.
Dirichlet.
It's in French.
In pencil parlor, this is a set vowel or 0 vowel boundary condition, I think. So
And
if
von
that
Neumann
is
is for derivative. Von Neumann is derivative, right?
Yes. And generally, I'm talking about f on the boundary equal to 0, but I guess any constant value here would be Dirichlet. Okay, here is that weighting thing I've been talking about, relative weight 1 to 1, because it has some optimal properties. and people call this restriction. And maybe I should say what you are seeing here. I start a new job at the end of the month, so I won't be able to do much on that. But I wanted to leave this in a state where anybody who's interested in that can take up the work that has been done and continue it. And so the things that took me longest to figure out with this method, I tried to document. And one of the things that took me longest to figure out is the nomenclature, because the nomenclature here is horrible. So I decided to the wild zoo of incomprehensible names, I decided to add my own nomenclature. And so I thought about coarse graining and fine graining, because that's something that I can understand, that's something you won't find anywhere else. What this document here is something I've checked in. It's under the doc directory, the subdirectory of the doc directory of the pencil code. And this thing here is formulated as a glossary. So at the same time, it tells you something about how the multi-grid methods work, how we implement them, and also about the nomenclature.
The wave Jacobi iteration is something like a SOR method, no? With a relaxation parameter.
What sort of method?
The parameter W here is
Yep.
something like a relaxation parameter, right?
I hope so, yeah, must be. I mean, what is W? Half or what?
It can be changed
So
value.
Typically,
Oh,
people
Yeah.
use 2/3.
Ah, yeah.
But I think you can also have that dynamical. Yeah.
Yeah. I have a-
Relaxation is one of these terms that I never remember which of these steps you really call relaxation. You restrict and you refine and you prolongate and you smooth and you relax. And in the end, you have just two operations. So I never get the mapping right.
Yes, I have a talk for you. A guy in Toulouse made a talk about solving a big linear algebra problem. And he made a comparison between Jacobi method, Gauss-Seidel, conjugate gradient, and SOR method. And there are some figures in the talk where you can see the difference for Laplacian, inversion of Laplacian of order 100 over 100. And that's really interesting for you in this case.
I'm interested, even if it's in French.
Yes, but you speak French very well, so no problem.
Okay, and then more nomenclature, but we've talked about the relevant stuff already. Now, going back from the coarse grid, or rather here, to the fine grid, as I said, is done by trilinear interpolation, or linear in the 1D toy model and trilinear in 3D. And the theory says that for a second order operator, the scheme has to be at least linear. And if you use something that's better than linear, if you use a quadratic or cubic interpolation scheme, you initially get better convergence. So you get down to 0 somewhat faster here, but then you just get things change and you just get the same convergence rate. So it doesn't buy you that much, and it has some numerical cost attached to it, and particularly some coding costs before you know that you really get it right. So I stuck with what people normally use for Laplacian with a trilinear interpolation. Okay. This is what I just outlined is implemented, and I'll show an example of how it works. There's all sorts of complications that will sooner or later harm us. One is that if you have an anisotropic grid, if delta x is significantly larger than delta y, for example, and you use the isotropic Laplacian. Another way of seeing that is you have a grid with delta x equal to delta y, that you have different weights in the d by dx squared and the d by dy squared of the differential operator. It's the same situation, just a different way of describing it. If that's the case, and And much larger here means a factor of 2 is enough to very clearly see the effect. Then the convergence of the scheme degrades drastically. And that can be understood, and I keep forgetting the details. That's discussed in all the literature. And there's basically 2 ways out. So one is called semi-coarsening. That means you don't always go to a coarser grid in all directions. You only do that, well, you do that selectively such that as soon as possible you get comparable grid spacings. That's an easy thing to do if you know in advance that this situation is there. So if you are out of luck if this is not because of the grid, but it's because maybe I should point here, if the different weight for the different directional derivatives is not because of the grid or something that you have under control, but because of something that evolves dynamically and can evolve structures, then you're out of luck with that method. But if it's just that you have a grid with non-isotropic axis ratio, the step ratio, for some practical reasons, because some other part of your physics is non-isotropic, then you can apply that, and then you can easily figure out: should I go to the coarser grid in this dimension, or is that dimension already significantly coarser, or is it similarly coarse to the one that I get for the other dimension? And then you just skip the coarse grading for that step, and then you go on from there. So I think for some of the most likely problems where we could run into this, that's a nice solution. An alternative is line relaxation or plane relaxation, where you don't do the iteration point by point, but you solve on a line or a plane at a time. So instead of solving, let's see, where do I have that? When you have the discretized version of your equation, instead of doing this, instead of solving on a zero-dimensional subspace, here we're just solving for the very point that we're using to scan through the volume. You take one of these equations and do the whole direction at a time. So you still put the y and z derivative stuff on the right-hand side to iterate, but you do all of this with a three-diagonal matrix. Now, for one dimension, that's fine. Three-diagonal systems are easy to solve. For 2 dimensions, you're basically back at the point where you started, and you need an efficient method to solve for a solved equation, even if it's now 2-dimensional and not 3-dimensional. But of course, we know such a method. You can do that with multigrid, and it turns out that you don't have to do the full 1-dimensional or 2-dimensional problem exactly, but you can just do one multigrid sweep there, and that's enough. So I would be astonished if that was very clear by how I explained it. But basically the message is this line relaxation or plane relaxation can be done, and it is conceptually the same as the whole method, and it can be relatively easily incorporated. It's just that you treat the dimensions differently. You first do something in a plane, and then you move on to the next plane. Basically, that's all there is.